For nearly a century, cosmology has described a universe born in fire, expanding through space and time, dominated by unseen components. The lambda CDM model has been extraordinarily successful, but every model rests on assumptions. What if cosmic redshift has another origin? What if time itself is not what we think it is? This is the Exochronous Universe, rethinking cosmology from first principles. Every star, every planet, every living cell, and every person who has ever lived is made from the same familiar building blocks: ordinary matter. It is so commonplace that we rarely stop to ask a remarkable question. Why does it exist at all? According to everything we have learned from modern particle physics, matter has a natural counterpart, antimatter, and under the extreme conditions believed to have existed in the early universe, matter and antimatter would be expected to form together in almost equal amounts. If that happened, almost all of it should subsequently have annihilated, leaving behind a universe filled with radiation, but almost no matter. Yet that is clearly not the universe we observe. Instead, galaxies exist, stars exist, we exist. Explaining this tiny imbalance between matter and antimatter is one of the deepest unsolved problems in modern cosmology. It is known as baryogenesis. The word baryogenesis simply means the origin of baryonic matter. Baryons are particles such as protons and neutrons. Nearly all of the visible matter in the universe is built from them. So baryogenesis asks a deceptively simple question. Why does the universe contain so many baryons, rather than equal numbers of baryons and antibaryons? Before we explore the proposed answers, we first need to understand why physicists believe this question arises in the first place. Antimatter is not science fiction. It is routinely produced in laboratories around the world. Every known particle has an associated antiparticle with the same mass, but opposite electric charge, and certain other quantum properties. For example, the electron has the positron, the proton has the antiproton. Whenever sufficient energy is concentrated into a small enough region, particle-antiparticle pairs can be created. This behavior has been confirmed countless times in high-energy physics experiments. Applying these same physical laws to the extremely hot conditions believed to have existed in the earliest moments of the universe leads naturally to an important expectation. Matter and antimatter should initially have been produced in almost equal quantities. It is important to note that this earliest period cannot be observed directly. Rather, this expectation comes from applying experimentally tested particle physics to conditions beyond those we can currently reproduce in the laboratory. Matter and antimatter cannot peacefully coexist indefinitely. When a particle encounters its antiparticle, they annihilate. Their mass is converted into energy, usually in the form of high-energy photons. Imagine beginning with 1 billion particles of matter and 1 billion particles of antimatter. After annihilation, nothing remains except radiation. Now imagine instead that there were just one extra matter particle. 1,000,000,001 matter particles and 1 billion antimatter particles. After almost complete annihilation, a single particle survives. Everything we see today, every galaxy, every star, every planet, ultimately traces its existence back to an imbalance remarkably similar to this. How large is this imbalance? Surprisingly, it is extraordinarily small. Cosmologists describe it using the baryon-to-photon ratio. This compares the number of surviving baryons with the number of photons in the universe. Today, most of those photons make up the cosmic microwave background discussed in our previous episode. Observations indicate that there is only about 1 baryon for every 1.5 to 2 billion photons. Although tiny, this ratio has been measured remarkably consistently using two completely different approaches. One comes from the cosmic microwave background, the other comes from the abundance of the light elements produced during primordial nucleosynthesis. We will explore those abundances in the next episode. The important point for now is that the asymmetry itself is strongly supported by observation. Its physical origin remains unknown. In 1967, the physicist Andrei Sakharov realized that any successful explanation would require three essential ingredients. First, physical processes capable of changing the total number of baryons. Second, interactions that distinguish, however slightly, between matter and antimatter. This is known as CP violation. Third, conditions in which the universe is temporarily driven away from thermal equilibrium. Remarkably, these three requirements are almost completely general. They do not describe one particular theory. Rather, they describe what any successful theory of baryogenesis must ultimately achieve. Over the past several decades, physicists have proposed a number of possible mechanisms. One possibility is electroweak baryogenesis, in which the asymmetry develops during a phase transition associated with the electroweak force. While elegant in principle, calculations suggest that the amount of CP violation present in the standard model appears too small to generate the observed asymmetry. Another possibility invokes new physics at much higher energies through grand unified theories. These models naturally permit baryon number violation, but the required particles have never been observed. A third family of ideas, known as leptogenesis, proposes that an asymmetry first develops among leptons before being partially converted into baryons by known electroweak processes. Leptogenesis has become one of the most actively studied possibilities. However, it too relies upon particles and interactions that have yet to be experimentally confirmed. Each of these ideas is grounded in serious theoretical work. None has yet been verified experimentally. The remarkable success of modern cosmology is that it can describe the evolution of the universe with extraordinary precision over billions of years. Yet one of its most fundamental questions remains unanswered. Why does matter exist at all? The observations are clear. The universe contains a tiny excess of matter over antimatter. Particle physics tells us the ingredients a successful explanation must contain, but the mechanism that actually produced this imbalance remains unknown. This is not a failure of science, it is simply where the frontier currently lies. Whatever cosmological model ultimately proves correct, it must explain why any matter survived. In our next episode, we'll examine what happened after that survival. As the universe continued to evolve, those remaining protons and neutrons combined to form the first atomic nuclei. Their abundances still carry a record of the earliest moments of cosmic history, and they provide one of the most powerful tests of any cosmological model.